that's what needs to happen. Because sometimes truth isn't good enough. Sometimes people deserve more. Sometimes people deserve to have their faith rewarded.
Because our device has many moving pieces, the modal analysis has to be done on several of the components. The main components we picked were the blade, the gear, and the motor. From our results, we find that the first resonant frequency that occurs to the blade is around 277 Hz, which is actually something we have to watch out for. The gear, on the other hand, doesn't have a resonant frequency to around 7,800 Hz, highly unlikely to happen. For the motor, the first resonant frequency occurs at 630 Hz, which, although it's a little high, is still something to be aware of.
A thermal analysis was made to see how hot each component got when a portion of its power rating was applied. We set two different convection loads on the interior and exterior surfaces and a thermal contact set on the gripping case, while applying heat power into the motor. The first iteration showed the grip to be too hot in the case to melt. In the second and third iteration, the addition of a grip and a change in materials led to lower temperatures in a structurally intact case.
We did a static analysis on a shell with a different load of 5, 20, 50, and 100 Newton applied on the top handlebar. Symmetric boundary conditions is also applied. Different boundary conditions are applied at the bottom shell utilizing split glaze function. After running analysis, the max stress happened in these areas, so we added a fillet right here. The stress concentrate reduced. For the final iteration, we added fillet in those areas to ensure that the sharp edge isn't causing problems. The results show that the maximum stress still happens at the corner of the handlebar, but does likely reduce at the bottom edge. Maximum displacement results on the top of the handlebar where the load is applied.
We performed several static analyses to assess the integrity of the jigsaw's blade. In case 1, a load of 250 newtons was applied upward on the blade tip. The counterbalance by the user led to the fixed constraint on the top face of the blade. On the other simulation, we applied the same load distributed over the blade's entire bottom face. The results for our first iteration showed yielding in both cases. The modifications made to the blade in the second iteration lowered the maximum von Mises stress by a factor of 9 for the first case and a factor of 7 for the second. Although the blade withstood yielding in the second case, buckling was still a concern.
Through regular usage of the jigsaw, the blade must be subject to forces along the cutting edges. High amounts of forces in the plane of the relatively thin flat section of the blade make it much more susceptible to buckling out of the blade. This is alleviated in the later iterations of the blade, which is thicker. The blade holder is more susceptible to failure through deformation than by buckling. By reinforcing the place where the connection to the blade and the connection to the gear train meet with a fillet, this is also prevented.